The coral reef is a living mosaic of movement and noise, bursting with color and tension. Every corner holds a game of survival. Ambush predators tucked beneath ledges, flickering schools of glassfish darting through shafts of sun, and crustaceans working tirelessly in sand-scattered silence. But nestled among these intricate dramas is an animal whose entire survival hinges on an evolutionary gamble, one so dramatic and inefficient that it borders on farce. The pufferfish does not flee. It does not fight. It inflates. At first glance, the pufferfish is unremarkable. A plump-bodied little swimmer with exaggerated eyes and a gentle, almost bewildered face. It navigates the reef slowly, propelled by fluttering pectoral fins and a trailing tail, like a balloon drifting through a breeze. But beneath this cartoonish appearance lies one of the most extreme defensive reflexes in the marine world. When threatened, the pufferfish gulps water, or air if out of water, expanding its elastic stomach to several times its normal size. In moments, it transforms into a floating spherical minefield covered in sharp, rigid spines. This isn't mere bluff. The sudden inflation can stop predators mid-strike, trigger their retreat, or make the fish too large to swallow. At least in theory. In practice, however, the strategy is a physiological catastrophe. Inflating is not a casual decision. It is a desperate, last-resort response that sends the fish into metabolic overdrive. The process floods its body with lactic acid, spikes heart rate, and can take hours to recover from. Worse, while inflated, the puffer becomes almost entirely immobile. It loses control over buoyancy, often drifting helplessly through currents or spinning in place, unable to steer. Some inflate too late and are caught mid-transformation. Others puff too soon, then slowly bob toward danger like an underwater parade float. Many predators, particularly experienced ones like groupers and reef sharks, quickly learn to wait. They recognize the puff as temporary. Once deflated, the pufferfish shrinks back to a manageable size and becomes vulnerable once again. In some reef systems, moray eels have been observed biting puffers, then releasing them briefly until the inflation ends, only to return for the real kill. It's a defense mechanism that works best against inexperience and loses potency with every failed attempt. Biologically, the puffer's mechanism is a marvel of adaptation. It lacks ribs and has a highly elastic stomach, capable of ballooning without rupturing. Its skin can stretch dramatically, and specialized muscles coordinate the rapid intake of water. Some species also possess tetrodotoxin, a potent neurotoxin concentrated in the skin and organs, capable of paralyzing predators and humans. This makes them among the most poisonous vertebrates on Earth. But tetrodotoxin doesn't help if the predator doesn't bite, or if the puffer misjudges the threat entirely. In captivity, puffers are infamous for misfiring. Sudden light changes, shifting decor, or even a curious snorkeler can trigger a full inflation. They've been observed puffing inside tanks, getting stuck in narrow pipes or filter inlets, and dying from the sheer stress of the event. In the wild, they can overinflate with air rather than water, a more dangerous variation that can lead to floating belly up at the surface, unable to expel the trapped gas. Recovery from such incidents is slow and not guaranteed. Juvenile puffers, still learning reef dynamics, are the most prone to overreaction. Their early inflations are clumsy, sometimes occurring in response to non-predatory fish or even swaying algae. It's a developmental stage steeped in panic. As they mature, most learn to calibrate, puffing only when escape is no longer an option. But even adult puffers have been seen inflating in response to their own reflection, or after bumping into coral. In a world of refined sensory systems and targeted responses, the pufferfish remains a slave to its dramatic instincts. Its entire strategy is built not on agility or awareness, but spectacle, and that spectacle has evolutionary costs. While puffers have relatively long lifespans for fish, sometimes over a decade, they live a life of constant tension. Each encounter could be their last. They are poor swimmers, clumsy navigators, and overly reliant on one extremely visible trick. Their coloration offers some camouflage, but not enough to deter larger predators. They do not school for protection. They do not ambush or flee well. They rely on intimidation in a realm where stealth and speed dominate. Yet for all their foolishness, puffers endure. There are over 120 species globally, thriving in tropical and subtropical seas, estuaries, and even brackish environments. Their ability to survive despite their limitations speaks to a deeper ecological truth. Success is not always about perfection. Sometimes it's about being just strange enough to be left alone. And in the reef, where everything eats and is eaten, weirdness can be its own survival trait. But to call the pufferfish clever would be misleading. Its panic response is costly, its strategy outdated in an ocean growing more dangerous. It cannot adapt quickly to human encroachment or invasive species. Pollution and habitat degradation increase stress triggers, leading to more unnecessary inflations and premature deaths. In a rapidly changing reef system, the puffer's reliance on shock and bloat may not be enough. Still, watching one inflate is unforgettable. It is a performance, half threat, half comedy, that encapsulates both the genius and absurdity of evolution. A creature so frightened of the world that it became a floating weapon, only to find itself more vulnerable than ever. In the silent theater of the ocean, the pufferfish plays its role with flair, even if the act leaves it spinning helplessly in the current, wondering what went wrong. Beneath the shallows of a warm tropical reef, the seafloor glows with slow, filtered sunlight, not in beams, but in pulses of shifting gold as waves above refract across coral heads and ridges of sand. Algae sway with the movement, bent gently by tidal rhythm, while butterfly fish weave between the coral's latticework, pecking at microflora too small to see. Crabs scuttle, wrasses patrol, and even the sluggish parrotfish grind methodically at stone. But among the ocean's constant motion, one creature defies the urgency, not with calculated stillness, but with the inertia of evolutionary surrender. The sea urchin does not move quickly, it does not hide, it does not fight. It simply exists, a spherical contradiction of armor and vulnerability, relying entirely on the passive threat of discomfort. To understand the sea urchin is to observe a creature that seems, on the surface, to have stopped trying. Covered in a dense forest of calcium carbonate spines, it presents itself as unappetizing, dangerous, and impassable. This defense is not subtle. The spines protrude in all directions, rigid and sharp, forming a living minefield across the seafloor. Some species, like the long-spined black diadema, stretch their quills out half a meter, shadowing the reef beneath. Others are squat and almost floral, with short, stubby spikes in hues of purple, red, or green. And yet, beneath the threat display, the animal is nearly helpless. Its soft, vulnerable body, which contains its organs, reproductive system, and primitive nervous structures, is tucked tightly beneath the dome of its shell. The spines aren't active weapons. They don't strike, chase, or paralyze. They merely are. They hope you get the message. Biologically, the sea urchin belongs to the echinoderms, a phylum that includes starfish, sea cucumbers, and brittle stars. Like its cousins, it operates through a hydraulic system of tube feet, thousands of tiny suction-capped limbs extending from its ventral surface. These feet help it move, albeit slowly, across rocks and sand. They're sensitive to light, pressure, and chemical cues, and some are even tipped with photoreceptors. But this complexity doesn't translate into strategy. Urchins often crawl in circles or directly into danger, even when equipped with the sensory tools to detect it. They've been found wedged in crevices too narrow to escape from, entangled in discarded nets, and in some tidal zones, stranded during low tide, where they desiccate and die beneath the sun. Their locomotion is uncoordinated and achingly slow. If flipped over by a passing fish, wave, or curious diver, the urchin begins an awkward ballet of recovery. It extends its tube feet, groping blindly at the substrate, slowly attempting to lever itself upright. This can take hours. Sometimes it fails entirely, leaving the animal exposed and motionless, a spine-covered dinner plate for any predator willing to risk the bite. Despite their appearance, many sea urchin spines are not lethal. Some break off easily, acting more like splinters than weapons. Others are hollow and venomous, capable of causing irritation, pain, or mild paralysis in small predators. But even these effects rarely kill. Instead, the defense depends on deterrence. The urchin survives not by winning but by being unappealing, and that appeal varies greatly. Some fish, like triggerfish and wrasses, have evolved techniques for flipping urchins, using bursts of water or precise pecking to expose the vulnerable underside. Octopuses use their dexterous arms to pry them open, while sea otters in temperate kelp forests smash them on rocks laid across their chests. These predators are not deterred by spines. They've adapted around them, and once that adaptation enters the ecosystem, the urchin becomes one of the least defended prey items on the reef. Ironically, sea urchins do have sensory tools that could, in theory, help them avoid these threats. Their tube feet detect pressure changes and chemical gradients, and some species have primitive eyes scattered across their spines, enough to differentiate light from shadow. They can perceive predators approaching, but their neural processing is minimal. Without a centralized brain, the sea urchin interprets threats slowly and reacts even slower. By the time it recognizes a shadow as dangerous, the danger is already upon it. It does not bolt. It does not contract. It merely pivots and begins its glacial crawl towards slightly less certain death. Yet, this apparent idiocy masks a surprising ecological importance. Urchins are critical grazers in reef systems. Their diet consists of algae, detritus, and decomposing organic matter. In healthy populations, they help keep algae in check, preventing overgrowth that can smother coral. But when predator populations decline, such as sea otters in kelp forests or triggerfish on overfished reefs, urchins multiply unchecked. They swarm across reefs and kelp beds in what are called urchin barrens, devouring everything in their path, leaving behind dead rock and skeletal coral. The same passive creatures that seem incapable of survival can, under the right circumstances, become ecological wrecking balls, and they don't even know they're doing it. Sea urchins are also reproductive overachievers. During spawning events, males and females release gametes directly into the water column, often in mass synchrony triggered by moon cycles or tidal changes. Fertilization is external and imprecise, but their sheer numbers guarantee success. A single female can release millions of eggs. Most won't survive, of course, eaten, drifted, or destroyed, but some do. And thus, the lineage continues, not through speed, cunning, or intelligence, but through volume. Their larvae, called echinopluteus, are planktonic, floating through the open ocean for days or weeks, developing slowly into their adult form before settling on the substrate. During this planktonic stage, they're almost unrecognizable, more like jelly-bodied kites than spiny spheres. It is here in this fragile, drifting form that urchins are most vulnerable. But again, their strategy is not avoidance, it is numbers. So what can we learn from a creature that lives in armor, yet seems utterly unequipped to use it? That shuffles toward danger and reproduces blindly, hoping the math works out? Perhaps that nature doesn't reward intelligence. It rewards persistence. The sea urchin survives not because it's brave or brilliant, but because it fits. It occupies a niche so well that its idiocy becomes irrelevant. It is both victim and villain, both essential and expendable. And yet when we watch it, spine against current, inching toward algae, oblivious to threat, we can't help but wonder if there's something else beneath that dome. Some ancient code that says keep going, even when everything else says stop. In the ocean, that may be the only intelligence that matters. Drifting silently through the warm coastal shallows of the Indo-Pacific, the box jellyfish is almost invisible. A transparent ghost beneath the surface, shimmering faintly with the motion of the tide. To the untrained eye, it appears lifeless, almost artificial, like a forgotten plastic bag drifting just beneath the sunlit ripples. But within that barely perceptible cube-shaped bell lies one of the most potent biological weapons the ocean has ever produced. Its tentacles, delicate and thread-like, can extend meters behind it in flowing curtains of death. A single brush against exposed skin can induce searing pain, skin necrosis, respiratory paralysis, and cardiac arrest, sometimes within minutes. And yet, for all this chemical sophistication, the box jellyfish itself moves like a creature with no idea where it is or what it's doing. Its anatomy is both ancient and contradictory. Box jellyfish, or cubozoans, lack a centralized brain. Instead, they possess a decentralized nerve net that processes input from an unusually complex set of sensory structures, including clusters of primitive eyes. Each box jellyfish has 24 eyes arranged into 4 rhopalia with 6 eyes per cluster. 2 of these are complex lens eyes capable of forming images. They can detect light, movement, and even obstacles. But what they do with this information is another question entirely. Unlike vertebrates, which integrate vision through a central processing hub, cubozoans have no such core system. Their sight is more like a fragmented surveillance feed, streamed to a nervous system incapable of full comprehension. The result is behavior that appears at once purposeful and chaotic. They pivot, pulse, and shift directions, but often collide into rocks, coral, and even each other. Observations in both the wild and controlled environments have revealed moments of stunning incompetence. Box jellyfish have been filmed swimming in tight, repeating loops, not as a strategic maneuver, but seemingly because their sensory input becomes stuck in a feedback loop. They may swim toward shadows instead of light, bump repeatedly into barriers, or sting inanimate objects by accident. Some individuals have even lashed their own tentacles, or the tentacles of conspecifics, triggering neurotoxic discharge on creatures they never meant to touch. Unlike aggressive predators that target prey with intention, the box jellyfish simply drifts and stings, a wandering minefield in search of accidental collisions. Despite their poor navigation, box jellyfish are active swimmers, a trait that separates them from their more passive cyphozoan cousins. Their bell contracts rhythmically, generating propulsion far more efficiently than most jellies. This allows them to move vertically through the water column, escape from shallow estuaries when salinity drops, or rise toward moonlit surfaces during nighttime foraging. But again, this mobility is undermined by directionless execution. Studies show that many individuals move in patterns resembling Brownian motion, random movement, more than coordinated migration. It's not unusual for box jellyfish to wash up en masse after being carried inshore by currents they fail to recognize or respond to. Their anatomy affords motion, but not orientation. Ecologically, they are ambush predators in name only. Their tentacles are lined with cnidocytes, specialized cells armed with nematocysts that fire harpoon-like structures loaded with venom. These structures can inject toxins that target ion channels in muscle and nerve tissue, causing excruciating pain and potentially fatal heart arrhythmias. Small fish and crustaceans caught in this net are paralyzed instantly, reeled into the jellyfish's central body cavity for digestion. Yet even this act lacks precision. The jellyfish does not seek prey actively. Instead, it trails its tentacles and hopes something swims into them. A tiny trigger hair on the conidocyte senses movement and chemical cues, not by intelligence but by mechanical response. There is no decision-making, no judgment. If you touch it, it fires. And if you are it, it still might. This randomness becomes especially apparent during bloom events. In certain conditions, warm water, abundant nutrients, and low predation, box jellyfish populations explode. Suddenly, hundreds or thousands fill coastal lagoons and beaches, drifting into fishing nets, clogging intakes at desalination plants, and swarming areas used for recreation. Most sting incidents occur not during predation attempts, but because the jellyfish was simply there, invisible until someone moved through their tentacles. They have caused school closures, tourism declines, and in rare cases, multiple human fatalities. Yet these events aren't coordinated attacks. They're consequences of poor awareness. The box jellyfish is a biological weapon with no off switch, no aim, and no memory of what it just did. Even their reproduction reflects this strange duality of elegance and oblivion. During the Medusa stage, males release sperm into the water, which females uptake through their bell cavity to fertilize eggs internally. A surprisingly complex form of sexual reproduction for such a primitive organism. After fertilization, the female expels planular larvae, which settle and transform into polyps, small sedentary stages attached to substrates. These polyps can asexually bud off more medusae, creating a new generation of stingers. The life cycle alternates between passive clinging and active floating, a dance of reproductive overdrive matched by almost no parental investment or control. And yet, for all its obvious shortcomings, the box jellyfish has survived for millions of years. Its venom, originally evolved to capture fast-moving prey like fish, is overkill against human physiology. But in evolutionary terms, overkill is still effective. The jellyfish is not a failure of design. It's a demonstration that life doesn't require intelligence to be lethal. In some regions, sea turtles have evolved resistance to the sting, grazing lazily on cubozoans without concern. But for most marine creatures, and certainly for humans, brushing against a box jellyfish means instant panic. In that sense, it holds an ecological role not unlike that of landmines, unseen threats that force wide behavioral changes in everything nearby. Its fragility is matched only by its lethality. A creature that cannot think, cannot learn, and often cannot avoid disaster, and yet one that continues to shape ecosystems, influence behavior, and command respect through chemical warfare alone. It drifts, stings, and dies, often within months, leaving behind no memory and no footprint, but a body count. To call it stupid is technically incorrect. It is non-cognitive. It is function without thought, power without purpose. And as it pulses through the sea, trailing its deadly veil, we are reminded that nature often values efficiency over elegance. The box jellyfish is not cunning, brave, or even aware, but it survives. And in a world as brutal and indifferent as the open ocean, sometimes that's enough. In the warm shallows of the Indo-Pacific, where the reef flickers in kaleidoscopic bursts of light and motion, the sea anemone rises like a surreal, slow-motion firework. Its tentacles sway in the shifting current, delicate and dangerous, each one armed with nematocysts that paralyze small fish on contact. This toxic fortress seems uninviting, even menacing, until, nestled within its swaying reach, a flash of orange and white darts forward, fins trembling, mouth agape, as if ready to take on the entire ocean. It is a clownfish, and it is furious. At what, no one can say. Perhaps a shadow, perhaps a passing shrimp, perhaps nothing at all. But the display is unmistakable. A flare of false bravado, overacted aggression, and theatrical defiance. Until, in an instant, it vanishes again into the safety of its anemone host. The clownfish, or anemone fish, is among the most recognized symbols of coral reef life. With its vivid coloration, erratic movements, and symbiotic relationship with sea anemones, it appears confident, clever, even charismatic. But beneath the charming exterior is an animal whose entire survival strategy is based on bluster, overdependence, and an inability to cope without its host. It is the biological equivalent of a loud alarm system with no actual defenses. Its strength lies not in itself, but in what it hides behind. The relationship between clownfish and sea anemones is indeed a marvel of mutualism, a classic example of co-evolution. The anemone offers the clownfish protection from predators via its venomous tentacles, which the fish has developed an immunity to by coating its skin in a protective mucus. In return, the clownfish defends the anemone from polyp-eating intruders like butterflyfish and provides nutrient-rich waste that benefits the host. It also fans the anemone's tentacles with fin movements, improving oxygenation. From an ecological standpoint, this partnership is a functional success, but it also creates a dependency so extreme that without their anemone, many clownfish cannot survive. Remove the host, and the fish either dies of stress or wanders the reef until it is picked off, unprotected and unprepared. Within its anemone, the clownfish performs its infamous act. When disturbed, whether by a diver's hand, a floating leaf, or a curious crustacean, it erupts in a frenzy of posturing. The display includes rapid charges, fin spreading, and a staccato movement pattern meant to look threatening. Yet the moment the threat closes in, the clownfish withdraws into the tentacles, sometimes quivering in place, peering out with wide, panicked eyes. It is a cycle of false dominance and immediate retreat. Studies have shown that this behavior has almost no deterrent effect on larger predators. It functions more as a bluff display within the limited context of its small territory. A behavior evolved for interspecies communication more than actual defense. This territoriality is equally ironic. Clownfish guard their tiny patch of reef with obsessive vigilance, despite its minuscule size, often no larger than a dinner plate. They will defend this area from other fish, from conspecifics, and sometimes from inanimate objects introduced by researchers. But this obsessive defense doesn't scale. They will not chase intruders beyond the perimeter of their anemone's tentacles. Their aggression is location-locked. They are tyrants within inches, cowards beyond. Unlike cleaner wrasses or butterflyfish, which navigate reefs freely and manage complex interactions across distances, clownfish exist in a permanent homebound state, rarely venturing even a meter away. Even their social structure is built on restriction. Clownfish live in small groups consisting of a dominant female, a sexually active male, and several juveniles. Their sex is not fixed. They are protandrous hermaphrodites, meaning they all start life as males. If the female dies, the dominant male changes sex and becomes the new matriarch. But this system comes at a cost. Subordinate males remain suppressed by social cues, their growth, hormone production, and reproductive potential stunted. If a higher-ranking individual dies, the next in line rapidly develops, filling the vacancy. This hierarchy is enforced with posturing and aggression, but rarely results in actual combat. Like their defense strategy, it's mostly threat displays and ritual, lots of flexing, little substance. Despite this apparent fragility, clownfish are not unintelligent. They exhibit spatial awareness, can recognize individual conspecifics, and even demonstrate rudimentary problem-solving in captivity. But these traits are tightly bounded by their environment. Unlike cephalopods or even damselfish, clownfish do not explore, innovate, or adapt well to change. They are, evolutionarily speaking, hyper-specialists. Their survival is predicated on the existence of a host, the structure of a reef, and the absence of large-scale disruption. Remove one pillar, and the entire strategy collapses. This dependence makes them uniquely vulnerable to environmental change. Coral bleaching events, ocean acidification, and rising temperatures do not just destroy coral. They affect anemones, and by extension, clownfish. In some reef systems, entire anemone populations have died off, leaving clownfish homeless. Studies show that many displaced individuals fail to integrate into new territories, even when viable anemones are nearby. They will instead hover over dead reef, displaying signs of stress, refusing to leave. Their instincts are not built for flexibility. Their boldness evaporates without the shelter of poison-tipped tentacles. And yet for all their dysfunction, clownfish remain successful, at least for now. Their larvae are planktonic, drifting on ocean currents for days or weeks before settling. This dispersal mechanism allows for recolonization of distant reefs and creates genetic mixing across large distances. In captivity, they breed readily and adapt well to artificial systems. They are among the most studied and aquacultured marine species, which has ironically protected them from over-collection pressures that threaten other reef dwellers. But in the wild, their fate is tightly linked to the health of their environment. Unlike generalist species that can shift habitats or diets, clownfish exist within one of the narrowest ecological lanes in the ocean. Lose the anemone, and you lose the clown. They are, in many ways, a living contradiction. Bold yet helpless, aggressive yet immobile, adaptive in design but inflexible in practice. They thrive within the rules of a system they cannot survive outside of. Evolution has crafted them into miniature specialists, loud defenders of a home they neither built nor control. In the theater of reef survival, they play their part with dramatic flair, charging, flashing, vibrating with fury, only to vanish, almost comically, into the swaying arms of their deadly landlord. And the reef, indifferent and ever-shifting, moves on. Beneath the vast blue canopy of the open ocean, where the sun penetrates in shafts that fade quickly into infinite depth, a shadow cuts through the water like a blade. It moves too fast for the eye to follow, not gliding but slicing, propelled by sheer muscular violence. This is a tuna, and it is one of the most efficient motion machines evolution has ever constructed. Streamlined like a missile, rigid-bodied and built for relentless propulsion, it lives in constant motion. It has no concept of stillness. To stop is to die. Yet for all its precision-engineered speed, the tuna is also a creature haunted by its own momentum, a predator governed by reflex, unable to slow down, prone to panic when confronted by barriers, confinement, or the unfamiliar. It is a Ferrari with no brakes and a twitchy driver. Tuna, members of the family Scombridae, are among the few bony fish capable of regional endothermy, the ability to maintain elevated body temperatures in critical muscle groups, such as the red muscle tissue used for swimming. This adaptation grants them powerful, sustained speeds and an almost unlimited cruising range. Their metabolism is explosive. Their hearts are proportionally massive, pumping oxygenated blood at volumes more akin to mammals than fish. Their gills are built for high-efficiency oxygen exchange, but only when water is continuously passing over them, which is why tuna can never afford to stop swimming. They are obligate ram ventilators. Without forward motion, their gills cannot function, and suffocation sets in within minutes. In essence, they are powered by motion, dependent on it not only for survival, but for breath. This constant forward drive defines every aspect of their life and every vulnerability. In the open ocean, their speed is a formidable asset. Yellowfin, bluefin, and skipjack tuna regularly cruise at 40 to 60 kilometers per hour, with bursts that can exceed 70. They chase down fast-moving prey like sardines and squid, outpace most predators, and traverse entire ocean basins in search of food and spawning grounds. But the cost of this speed is a brain wired for urgency, not judgment. When spooked, cornered, or confined, tuna react with catastrophic force. In fishing nets, they thrash and bolt in all directions. In tanks, they collide with glass or walls, sometimes at full speed, cracking vertebrae or rupturing swim bladders. Death by panic is not rare. It is a design flaw born of an evolutionary arms race that prioritized acceleration above all else. Even in the wild, this panic impulse can be fatal. Tuna often rely on visual stimuli to locate prey or avoid obstacles, but they process information in bursts, reacting to motion more than context. Researchers have documented tuna attacking reflective objects, debris, and even other fish accidentally. In some cases, high-speed chases end in blunt impact with coral heads, boats, or the hulls of underwater rigs. Unlike ambush predators, which assess before acting, tuna are wired to respond first, recalibrate later, if they survive the encounter. Their behavior is governed not by calculated choice, but by a kind of biological tunnel vision that only makes sense in the unbroken horizon of the pelagic zone. Ecologically, tuna play a critical role in ocean food webs. As apex mesopredators, they control populations of smaller schooling fish, transfer energy vertically across trophic levels, and serve as prey for larger marine hunters including sharks, billfish, and even orcas. Their migrations, often seasonal, sometimes transoceanic, connect disparate marine ecosystems, fertilizing regions with waste and influencing the distribution of both prey and predators. Bluefin tuna, for instance, spawn in the warm waters of the Gulf of Mexico and the Mediterranean, but feed in the colder, nutrient-rich North Atlantic. These journeys, often thousands of kilometers long, require metabolic control and endurance rivaling that of migratory birds. Yet when disrupted, such as by bycatch nets or shipping lanes, the tuna's built-in response is not strategic evasion. It is frantic, chaotic escape behavior. This mismatch between power and judgment is especially evident under human pressure. Tuna are among the most heavily exploited fish on the planet. Their value, particularly bluefin species, has led to industrial-scale fishing that targets them at every life stage. Purse seiner nets, long lines, and drift nets don't just trap tuna, they provoke them. Once ensnared, the fish launch into escape behaviors that often cause fatal injuries long before they can be landed or released. Their bodies, so finely tuned for motion, are fragile under blunt force. Their skin tears easily under abrasion. The same muscle that powers their flight becomes a liability in confinement. Even transport to fish farms can prove disastrous. Tuna require constant swimming, precise oxygenation, and minimal stress. Fail any of these, and they die, quickly, sometimes en masse. And yet, despite their vulnerabilities, tuna persist. Their reproductive strategy hinges on volume. A single female can release tens of millions of eggs during a spawning event. Fertilization is external and uncontrolled, leading to vast numbers of larvae, most of which are lost to predation or environmental failure. Those that survive grow rapidly, feeding aggressively, and migrating long distances even as juveniles. Their lifespan varies by species. Yellowfin live up to 8 years, skipjack less, and bluefin can reach over 30. Over that time, they may cross oceans multiple times, facing temperature gradients, changing salinity, and evolving predator fields. And still, their primary tools remain unchanged: speed, stamina, and a nervous system wired to flee at the slightest twitch. Their vulnerability to noise pollution, thermal changes, and oxygen depletion is now becoming more visible. Tuna, like other pelagic species, are sensitive to thermoclines and oxygen minimum zones. As oceans warm and deoxygenate, their vertical range becomes compressed. They are forced into narrower bands of survivable habitat, often closer to the surface, which increases their exposure to fisheries and surface threats. These spatial shifts can disrupt entire food chains as tuna chase prey into unnatural zones or fail to find them altogether. And through it all, their evolutionary reflex remains the same: keep moving, keep fleeing, keep chasing, even when the ocean itself turns against them. To witness a school of tuna in motion is to see pure kinetic grace. They swim in coordinated arcs, shimmering in flashes of silver and blue, tight as a murmuration of starlings, yet driven by the physics of water and muscle rather than air. But it is also to watch a system pushed to its limit. Every twitch of the tail is a calorie spent, every reaction a bet placed, and when that bet goes wrong, when the predator turns out to be a propeller blade or the lighter trap, the result is not an adjustment, but a catastrophic burst into oblivion. Tuna are not fools in the sense of incompetence. They are specialists, peak performers built for a narrow window of environmental conditions. Their problem is not intelligence, it is rigidity. They have no off switch, no curiosity, no adaptive pause. And as the ocean becomes more chaotic, as the threats become less predictable and more anthropogenic, that rigidity turns from asset to liability. In the theater of marine life, tuna are the sprinters cast in a marathon. They are astonishing, overwhelming, and sometimes tragic. Speed without strategy, strength without caution, and always, motion without rest. In the dappled twilight of the seafloor, where shafts of filtered light break through drifting sediment to illuminate patches of algae-stained sand and tangled rock, the cuttlefish moves like a question mark. It glides not in straight lines, but in pauses and half-turns, pulsing forward with the rhythmic undulation of its lateral fins. There is no splash, no sound, no warning. It is there, and then it isn't, vanishing into a swirl of color, texture, and motion so rapid and seamless that it defies understanding. One moment it's rock, the next it's rippled kelp. Then without hesitation, a blur of electric zebra stripes pulses across its back. To the casual eye, this display is extraordinary. But for the cuttlefish, it is simply another misfire in a life lived between genius and confusion. Cuttlefish, members of the class Cephalopoda, are closely related to squids and octopuses. They possess one of the most advanced nervous systems among invertebrates, with a brain-to-body mass ratio approaching that of some mammals. Their skin is lined with chromatophores, pigment-filled sacs that expand and contract under neural control, along with iridophores and leucophores that reflect and scatter light, allowing them to produce dazzling displays of color and contrast in fractions of a second. They can mimic patterns, shadows, even polarized light, a spectrum of perception invisible to human eyes. Their skin, in essence, is a screen controlled by thought. And yet, for all this mastery of disguise, cuttlefish often appear to have no idea what they're trying to say. Their camouflage is not just visual trickery, it's functional survival. In predator-rich environments, cuttlefish use background matching to blend into sand, coral, or seagrass. Their ability to not only mimic, but morphologically sculpt their body, raising skin papillae to match textures, places them among nature's most versatile shape changers. But this system is governed by reflexive pattern recognition, not reason. A cuttlefish does not assess camouflage like a painter evaluates a canvas. It reacts to surrounding contrast, edge detection, and environmental clutter, which is why, when placed in aquariums with artificial decor, they often attempt to mimic the plastic plants, or worse, the glass itself. They flash colors at their own reflection. They freeze against smooth acrylic backgrounds in high-contrast zebra stripes, standing out like actors in the wrong scene. The software is powerful, but the interface is buggy. In the wild, this leads to both brilliance and comedy. Cuttlefish sometimes initiate complex courtship patterns, rhythmic waves of shifting light and banding, in response to approaching predators. These mating signals, when misdirected, not only fail to deter the threat, but likely confuse it. In moments of high stress, some individuals emit a chaotic strobe of color bursts that seem less like a warning and more like a sensory overload gone haywire. Researchers speculate that these may be anti-predator displays meant to startle, but more often than not, they resemble a magician performing card tricks while being mugged. Male cuttlefish exhibit one of the more bizarre behaviors in the cephalopod world: deceptive signaling. In the presence of dominant males, some smaller or lower-ranked individuals will disguise themselves as females, changing both color and body posture to mimic female patterns, to sneak past rivals and mate with guarded females. It's an extraordinary example of behavioral strategy and sexual deception. But like all such tactics, it's prone to error. Some males forget to switch back, continuing to signal as females even after courtship begins, leading to confusion or aggression from actual mates. In some observed cases, cuttlefish have attempted to court males while still dressed in female patterning, resulting in mutual displays of misinterpreted intent. In captivity, where the social and environmental context is removed or dulled, this confusion compounds. Cuttlefish have been known to ink themselves in response to changing tank lighting, to initiate threat displays at their own shadows, and in some cases, to remain motionless for hours after releasing ink, seemingly convinced they are still invisible. Unlike octopuses, which use ink to cover their retreat with a quick burst and flee in coordinated escape maneuvers. Cuttlefish sometimes release ink without moving, as if the ink itself were the strategy. The cloud dissipates, and the cuttlefish hovers in place, exposed and inert. It is misfire camouflage, a magician who vanishes with a puff of smoke and remains center stage. Their feeding behavior reflects similar contradictions. Cuttlefish are ambush predators, using their two long, prehensile feeding tentacles to strike at prey, primarily small fish, shrimp, and crabs. They stalk with astonishing patience, using chromatic mimicry to approach undetected before unleashing a rapid lunge, but their precision varies. Some individuals fire too early, striking nothing. Others misjudge the angle and retract tentacles awkwardly, adjusting posture and trying again with visible hesitation. In studies, cuttlefish have been shown to adapt strike angle based on prey behavior, suggesting complex neural modeling, but also to fall into repetitive loops, reattempting failed strikes without adjusting distance or approach. Intelligence, in their case, seems more like a swirling cloud of potential than consistent performance. Their ecological role, however, is undeniable. Cuttlefish serve as both predator and prey across reef and soft-bottom ecosystems. They regulate populations of crustaceans and juvenile fish, and in turn are hunted by dolphins, sharks, seals, and even seabirds. Their life history is short, typically only 1 to 2 years, and ends dramatically. After mating, both males and females rapidly decline, their bodies breaking down in a final cascade of reproductive effort. During this senescence phase, cuttlefish often display erratic behaviors, mistimed camouflage, failed strikes, repeated inking, and moments of apparent confusion. Death comes not with stillness, but with a slow unraveling of faculties, a magician forgetting how the tricks work. And yet, even in decline, their bodies are coveted. The internal shell of the cuttlefish, the cuttlebone, is buoyant and used by the animal for precise control over depth through gas regulation, a marvel of natural engineering. After death, it floats to shore, where it becomes food for birds and reptiles, or used in aviculture to provide calcium. The magician's final prop continues serving long after the act has ended. The cuttlefish is not a fool. Its behaviors are not the result of low intelligence, but of over-specialization in a world that changes too fast for instinct to keep up. Its confusion is not stupidity, but the cost of processing too much sensory information in a system optimized for immediate reaction, not reflection. In a stable environment, it thrives, adaptable, stunning, precise. But in the unpredictable, in the artificial, in the unfamiliar, its genius turns to farce. It is a creature of brilliant instinct and limited comprehension, a reminder that complexity does not always equal clarity. And as it fades into its chosen background, color shifting into stone, sand, or coral, we are left not with certainty, but with wonder. The magician disappears, the illusion perfect, even if the reason behind it remains a mystery. In the shadowed crevices of the reef, where sunlight thins to soft twilight beneath ledges and beneath overhangs crusted in sponge and coral, the ocean seems to breathe in hushed rhythms. It is here in these dark, narrow sanctuaries that the moray eel waits. Coiled like a spring, its long, muscular body barely visible except for the grim face protruding from the shadows. Jaws agape, teeth exposed in a fixed grimace. This posture is not aggression, though it appears so. The eel is not snarling, it is breathing. Like many reef fish, the moray lacks a buccal pump to actively draw water across its gills, and so it must open and close its mouth constantly, pushing oxygen-laden water through its pharynx. The result, however, is a look of perpetual hostility. For a creature already cursed with poor eyesight and a short temper, it does little to improve its social standing. Moray eels, comprising over 200 species in the family Morainidae, are solitary ambush predators that inhabit reef crevices, rocky substrates, and underwater caves throughout tropical and subtropical seas. Their long, snake-like bodies, devoid of pelvic fins, covered in a thick, mucus-secreting skin, allow them to wedge deeply into the labyrinthine cracks of coral structures. This preference for confinement defines their entire behavioral repertoire. The moray is, by nature, a creature of hiding. It spends upwards of 90% of its life tucked inside its den, peering out with watchful unease. It is not patrolling nor socializing. It is waiting, not out of patience but paranoia. When prey comes close, A passing damselfish, an unaware crustacean, the eel lunges forward with speed that belies its usual stillness. The jaws snap shut with incredible force, aided by one of the most bizarre feeding mechanisms in the fish world. Unlike most teleosts, which rely on suction to engulf prey, moray eels possess a second set of jaws, pharyngeal jaws, located deep in the throat. Once the outer jaws seize the victim, these inner jaws thrust forward, grab the prey again, and drag it backward into the digestive tract. It is a process more reminiscent of horror films than fish biology, and it makes retreat from a moray's bite nearly impossible. But for all this anatomical ingenuity, the moray eel's execution often falters. Its vision is poor, relying mostly on light contrast and general movement. It cannot resolve detail well, nor does it distinguish between threat and opportunity with much precision. As a result, morays frequently misjudge the size, position, or identity of their target. They snap at shadows, strike at reflections in aquarium glass, and in many cases, bite divers, photographers, and even scuba gear with no provocation. These incidents are rarely defensive in the biological sense. More often, they are errors of perception, false positives triggered by movement too close to their personal space. The reef may be home to thousands of species, but the moray eel tolerates few of them near its den. This distrust extends even to potential allies. Many reef fish maintain mutualistic relationships with cleaner species, smaller fish or shrimp that remove parasites, dead skin, and debris from their bodies. These interactions are not just tolerated but sought after, forming essential components of reef health. Morays, however, often misread these delicate overtures. Cleaner wrasses or shrimp attempting to enter a moray's mouth, an act that other species accept passively, are sometimes greeted with a violent snap, ending the partnership before it begins. Some morays do engage with cleaners successfully, but even in these cases, the trust is shaky. One twitch, one false move, and the alliance collapses into violence. Their defensiveness is not entirely unjustified. Morays, despite their fearsome reputation, are vulnerable in open water. Their narrow body plan and lack of strong pectoral fins make them poor swimmers, awkward and slow when fully exposed. This limitation forces them to overinvest in shelter. They choose dens with few escape routes, often twisting into tight spirals deep within rock fissures. But these very refuges can become prisons. Morays have been found dead, their bodies decomposing inside crevices too narrow to escape after injury or entrapment. They can become wedged during feeding lunges or panicked retreats. When frightened, they rarely calculate. They thrash backward blindly, sometimes sealing their own fate. Reproductive behavior offers little relief from this tension. Most morays are broadcast spawners, releasing gametes into the open water during brief spawning aggregations, a rare moment of collective exposure for a species that otherwise avoids its own kind. The larvae, known as leptocephali, are transparent, ribbon-like drifters that spend months in the plankton before settling and transforming into juvenile eels. During this period, they are utterly unlike the adults, passive, delicate, translucent, a ghostly prelude to the suspicion and aggression of their future selves. Ecologically, morays occupy a strange niche. They are apex ambushers within their immediate radius, able to take down prey nearly their own size, yet also function as scavengers and opportunists. In some regions, they form cooperative hunting alliances with other species, notably groupers, who signal morays to flush prey from hiding. This behavior suggests some capacity for interspecies coordination, but its consistency and intent remain debated. More often, morays are antisocial, intolerant of conspecifics and competitors alike. Territorial disputes are resolved not through display, but through direct aggression. Bites between morays can be brutal, resulting in torn fins, severed tails, or worse. Their physiology reflects their solitary, cryptic lifestyle. They lack scales, relying on a mucus layer that protects them from abrasion as they squeeze through sharp coral and rock. This mucus also contains antimicrobial compounds, shielding them from infection in their high-contact environment. Their elongated nostrils give them acute chemosensory capabilities, compensating for their poor vision. They can detect prey hidden beneath sand, rotting inside crevices, or drifting in the current. Though again, this olfactory sensitivity does not always prevent mistakes. Many morays will strike at objects that simply smell like prey, regardless of shape or size. In captivity, their behaviors become even more erratic. Confinement exacerbates their territoriality. Tank mates are often seen as threats or meals. Feeding events become frantic, aggressive scrambles, with morays striking at glass walls, feeding tongs, or even their own coils. When stressed, they sometimes refuse to eat for weeks or thrash violently in attempts to escape, injuring themselves in the process. Their intelligence, which includes spatial memory and conditioned feeding responses, is offset by a hair-trigger nervous system that treats every anomaly as a threat. And so the moray eel endures, not by finesse but by force of instinct. It is a creature honed for a specific environment with little tolerance for deviation. It survives not through adaptability, but through control. Control over territory, over space, over what is and is not allowed near its mouth. But this control is brittle, and the cracks are evident. When forced into the open, when challenged by novelty or noise, the moray does not adapt. It reacts, and sometimes those reactions turn fatal, not for its enemies, but for itself. It is easy to mistake the moray eel for a villain, a monster lurking in the dark. But it is not malicious. It is anxious, miswired, and overarmed. A relic of reef evolution that succeeded not by understanding its world, but by pushing it away. In the theater of coral life, it is not the hero, nor the antagonist, but the anxious hermit in the wings, snapping at anyone who gets too close. And sometimes in that darkness, the most dangerous thing is not what lurks, but what doesn't want to be found. In the hushed stillness beneath an overhang of ancient coral, where only filtered shafts of blue light pierce the gloom and the water seems to hold its breath, the grouper hovers. It is a leviathan compared to most reef inhabitants, thick-jawed, barrel-bodied, a muscled shadow dusted in mottled patterns of sand and silt. And yet, for all its bulk and jaw power, the fish barely moves. Its pectoral fins twitch with the barest effort, maintaining position in the gentle surge. There is no hunt underway, no threat responded to. The grouper simply lingers, passive, as though hoping the ecosystem will forget it exists. Groupers, members of the subfamily Epinephelinae, are formidable ambush predators that inhabit coral reefs, rocky coastlines, and continental slopes in warm and tropical waters around the world. Biologically, they possess the tools of top-tier hunters. Jaws capable of explosive suction, a throat lined with crushing pharyngeal teeth, and the mass and power to dislocate joints in a single bite. But their evolutionary strategy is not built on speed, finesse, or cunning. It's built on stillness, a kind of underwater inertia that has made them simultaneously effective and surprisingly vulnerable. Hovering among rocks and ledges, groupers wait. They are sit-and-strike predators, relying on the element of surprise rather than any form of pursuit. Their bodies are not shaped for sprinting. Broad and compressed laterally, they trade streamlining for anchorage, capable of powering a quick burst but not sustaining a chase. When prey wanders close, a passing damselfish, a slow crustacean, an unfortunate cephalopod, the grouper's mouth opens in a sudden hydraulic expansion. Water rushes in with such force that the surrounding pressure gradient collapses, pulling the prey into a vacuum. It's one of the most powerful suction strikes in the animal kingdom. But when mistimed, it is also one of the most tragically sluggish. In some encounters, groupers lunge late or open their mouths prematurely. The strike becomes a slow-motion collapse rather than an explosion. Prey darts away unharmed, while the grouper remains suspended, mouth agape in post-strike confusion. Studies have shown that groupers often miss fast-moving prey entirely, especially in clear water or during higher light conditions when shadows betray their presence. They excel at ambushing the careless, not outsmarting the cautious. This clumsy brilliance extends to their behavior around humans. Groupers are notoriously curious. In areas frequented by divers or fishers, large individuals often approach slowly, unthreatened, as if seeking interaction. This trait makes them unusually susceptible to spearfishing. Unlike other fish that dart away at the first sign of disturbance, groupers will sometimes hover motionless, observing the diver with what appears to be calm curiosity, right up until the moment they are speared. In overfished reefs, this naivety has led to population crashes. Their confidence is not based on intelligence or wariness. It is based on size, a misplaced assumption that their mass alone affords immunity. Their ecological interactions further blur the line between apex predator and docile giant. In cleaning stations, critical microhabitats where fish congregate to have parasites removed, groupers line up like schoolchildren. They open their mouths and gill flaps, allowing cleaner wrasses and shrimp to enter and do their work. But these sessions are not always harmonious. In some reefs, smaller wrasses have been observed bullying groupers, nipping at sensitive areas or stealing mucus instead of cleaning. The groupers rarely retaliate. In fact, they sometimes appear confused, flinching but not moving, as if unsure whether the discomfort is part of the service. Their passive demeanor, effective in ambush, becomes disadvantageous in negotiation. They are predators who let others poke at their teeth. Groupers are protogynous hermaphrodites, born female, with some individuals transitioning to male later in life, often when they reach a certain size or social position. This transformation is complex, involving shifts in hormonal regulation, behavior, and reproductive anatomy. During spawning seasons, groupers aggregate in massive numbers to form temporary breeding groups, often at traditional sites passed down across generations. These aggregations, spectacular in scale, are also their Achilles heel. Fishers, aware of the predictable timing and location, have exploited these events to devastating effect. Entire spawning populations have been wiped out in a single season. The groupers' tendency to gather, to linger, to trust their old rhythms, all become liabilities in a world no longer ruled by balance. Despite their flaws, groupers play a pivotal ecological role. By controlling populations of smaller reef fish, they help maintain community structure and prevent cascading effects from prey overpopulation. Their size and longevity, some species live over 30 years, make them reservoirs of genetic resilience. But their slow growth and late maturity also make recovery painfully slow. Conservation efforts now include seasonal fishing bans, marine protected areas, and community-led reef monitoring, all designed to give the grouper time to grow, to spawn, to relearn caution. In artificial environments, groupers are even more surreal. In captivity, they often imprint on keepers, following them around the tank, sometimes even accepting food directly from tongs or hands. They learn feeding times, become responsive to motion cues, and display recognition patterns that suggest complex associative memory. Yet their behavior remains reactive rather than proactive. They do not explore, they do not invent, they wait. This paradox of immense physical power coupled with behavioral passivity makes the grouper a strange emblem of reef life. It is both dominant and docile, aggressive and inattentive. In natural systems, its style of predation works well. It removes the incautious, the unlucky, the distracted. But in altered systems, those disrupted by human noise, light and extraction, the grouper lags behind. Its instincts were carved in eras of balance. Today, they leave it adrift in a world that demands swiftness, suspicion and adaptability. To watch a grouper hover is to watch ancient strategy hold its breath. It is a fish that believes deeply in the effectiveness of stillness. But the modern ocean is not still. It is crowded, fast, and often merciless. And the grouper, the big baby of the reef, finds itself outpaced by creatures smaller, swifter, and less trusting. It is not unintelligent. It is, in many ways, overconfident. A slow heavyweight in a game now played by lightweights. And sometimes, its greatest strength, inertia, becomes its greatest flaw. The grouper waits. But what it waits for may already be gone. The coral reef is not a quiet place. Beneath the turquoise veneer of calm, it hums with tension, light and color. A labyrinth of life in constant motion. Shoals flicker like mirrored clouds, predators ghost between shadows, and the sharp staccato of snapping shrimp crackles in the shallows. Amid this density of purpose and coordination, one figure glides like a living contradiction. Broad, slow, and strikingly colored, the Napoleon wrasse, also known as the humphead wrasse, drifts into view with the ponderous grace of a creature too big to sneak, too decorated to camouflage, and too confused to care. At over 2 meters in length and weighing up to 180 kilograms, it is the largest member of the wrasse family, and arguably the most absent-minded. To see a mature Napoleonfish up close is to be drawn in by its surreal proportions. Its face, shaped like a sculpted anvil, is dominated by a bulbous forehead that rises in a sweeping dome, the Napoleon hump from which it earns its name. Iridescent blue-green scales shimmer like wet paint, interrupted by intricate maze-like markings that run across the cheeks and pectoral fins. Its eyes are large and expressive, scanning constantly and independently in opposite directions. Yet this extraordinary visual system, theoretically capable of rich spatial awareness, often results in paradoxical behavior. Divers and researchers have routinely observed these giants blundering into coral outcroppings or bumping into reef ledges as if unsure of their own dimensions. It is not uncommon to see a Napoleonfish in full exploratory motion turn suddenly and collide squarely with the reef it was just navigating. This peculiar lack of spatial caution isn't due to poor vision, quite the opposite. Napoleonfish possess color vision, depth perception, and a well-developed visual cortex for a teleost fish. But their immense size and awkward body plan don't lend themselves to precise maneuvering in the tight spaces of complex reef structure. Instead, they glide like airships, forcing smaller species to scatter in their wake, moving with the kind of confidence that suggests awareness, but not necessarily understanding. Foraging offers another glimpse into this strange marriage of power and absent-mindedness. Napoleonfish are among the few reef fish capable of preying on hard-shelled or venomous animals. Their powerful jaws can crush crustaceans, sea urchins, and even toxic boxfish. They are especially fond of mollusks, including giant clams, some of which weigh over 200 kilograms and require immense jaw strength to pry open. Yet despite their capability, Napoleonfish often display a curious lack of follow-through. Individuals have been observed retrieving a clam, swimming a short distance with it, then dropping it, only to search for it again moments later, clearly disoriented about where it fell. In some instances, they've been seen pausing mid-hunt, scanning with their bulbous eyes, only to drift away as if the objective had completely vanished from memory. In captivity, their eccentricities become more pronounced. While they can learn feeding cues and respond to handlers over time, their memory retention appears inconsistent. They may associate a diver with food one day and swim away indifferently the next. Studies in aquaria have found that while they are capable of basic associative learning, they require repeated exposure over extended periods and often regress without regular reinforcement. In comparative cognition tests with other reef fish, including wrasses and damselfish, Napoleonfish rank lower in problem-solving speed and spatial recall. It's not that they lack intelligence, rather their cognitive faculties seem diffused across too many stimuli, as if they process the world in fragments rather than cohesive sequences. Social behavior offers yet another lens into this disjointed intelligence. Napoleonfish are protogynous hermaphrodites, meaning all individuals are born female, with some transitioning to males as they mature. Dominant males often establish harems and defend territories, but the species is generally solitary. Their social hierarchies lack the precision of cleaner wrasses or angelfish communities, and interactions are often slow, awkward, and seemingly accidental. Males will patrol their territories in slow arcs, occasionally flashing color displays or extending fins. But these gestures are sometimes misdirected or poorly timed. On several occasions, observers have noted males performing courtship displays to the wrong species, or initiating dominance posturing with no visible rival in sight. Despite these peculiarities, Napoleonfish play an essential ecological role. As generalist predators, they help regulate populations of hard-shelled invertebrates and toxic species that few other predators can consume. This includes crown-of-thorns starfish, coral predators whose outbreaks can devastate reefs. By preying on such species, Napoleonfish act as inadvertent reef stewards, their scattershot diet reducing pressures that would otherwise tip the ecosystem out of balance. But this ecological value is undercut by their behavioral quirks. They are slow to respond to threats, easily approached by divers, and show little wariness even in regions with active fishing pressure. This has made them prime targets in the illegal live reef fish trade, particularly for the luxury seafood market in parts of Asia. Their sluggishness and curiosity, traits that once served them in predator-scarce environments, now render them highly exploitable. Their conservation status reflects this vulnerability. The Napoleonfish is listed as endangered by the IUCN, with populations declining due to overfishing, habitat loss, and limited reproductive output. Females mature slowly, and the transition to male can take years. Aggregation sites, used during spawning events, are predictable and easily overfished. In some regions, these sites have been completely depleted. Efforts to breed them in captivity have met with limited success, in part because of their size and slow reproductive cycle, but also because of their erratic behavior under artificial conditions. Still, there is something majestic about the way they move, as if immune to urgency. They do not dart. They do not flee. They glide through their environment like ancient sentinels, as if following a logic too slow for the fast-paced world around them. And perhaps therein lies their true evolutionary strategy, not agility or cunning, but scale, durability, and sheer resilience. They do not need to outthink the reef, only to endure it. And yet, endurance alone may no longer be enough. The modern ocean is a place of speed, noise, and extraction, an ecosystem accelerating beyond the comprehension of those adapted to stillness. For the Napoleonfish, that acceleration is both confusing and dangerous. What was once harmless curiosity is now a liability. What was once a harmless detour mid-hunt is now a missed opportunity for survival. Its greatness lies not in tactical brilliance, but in a kind of evolutionary grandeur, a testament to the power of bulk and blunder in a world that once allowed such indulgences. To watch it now, bumping into coral, pausing mid-hunt, forgetting its own clam, is to glimpse a creature that is not stupid, but misaligned. It is not lost, just lagging behind in a world that no longer waits. A reef titan, built for a slower, quieter ocean, still drifting with confidence but no longer entirely sure why. In the silence of the deep, where water pressure crushes and visibility dims, the ocean holds its secrets tightly. It is a place of design, elegant, brutal, efficient, where evolution has etched function into flesh over hundreds of millions of years. And yet, for every streamlined shark and stealthy octopus, for every hunter honed into an apex killer, there are others, those whose methods don't seem to make sense. Creatures that bumble, flinch, flail and fumble through the rules of natural selection, and yet somehow endure. They are the awkward edge cases of evolution, the deep-sea dunces. Across this strange and vibrant ecosystem, these animals don't win with speed or intelligence. They win by being just functional enough, often by accident. Consider the pufferfish, whose entire defense hinges on a panic-induced inflation so inefficient it often leaves it stranded, floating and helpless, a literal balloon in the surf. It can't outswim its predators, can't hide, and must inflate with comical urgency when startled, even by its own reflection. And yet, its spikes and neurotoxin are just intimidating enough to keep it off the dinner menu most of the time. Clumsy, awkward, easily spooked, but not extinct. Then there's the sea urchin, a creature with no real brain, no weapons and no plan. Its strategy is static. Sit still, be spiky, and hope nobody wants to deal with the hassle. Flip it upside down and it might spend hours trying to right itself. Leave it near the tide line and it will bake in the sun like a stone. It crawls with an army of tiny suction cup feet and primitive light sensors, often wandering straight into trash, nets, or shallow pools of death. Yet in the right numbers, it can overgraze entire reefs, triggering ecological collapse, a dull-witted bulldozer that doesn't even know it's moving. More dangerous, but no less oblivious, is the box jellyfish, a floating nerve net armed with some of the most lethal venom on Earth. It glides with ghostly detachment, trailing tentacles that can induce heart failure in humans in less than 5 minutes. But for all its biochemical deadliness, the jellyfish itself can't steer, can't learn, and can't aim. Its eyes can detect light and shadow, yet it drifts into beaches, rocks, and even its own kind, often stinging without purpose. It's not a hunter. It's a hazard. And evolution has let it persist not because of a sharp mind, but because a lack of one has never slowed it down. Meanwhile, the clownfish shouts from its poison tentacle palace, charging at crabs and divers alike with theatrical bluster, only to retreat into the safety of its host anemone seconds later. It lives in a patch the size of a dinner plate, and often dies if displaced, unable to adapt or even leave its comfort zone. Loud, territorial, and overdependent, the clownfish is evolution's version of a noisy neighbor who never leaves home, and whose entire life is lived inside borrowed walls. Then there's the tuna, a biological rocket ship that must swim constantly or suffocate. It is built for speed, with muscles designed to fire like pistons and a cardiovascular system that rivals that of small mammals. But this gift is a curse. In captivity or nets, tuna often panic and ram into walls until they die. In the wild, they can overexert themselves to death or swim into boats chasing bait they mistake for prey. For all their might, their minds can't match their motion. They are the sprinters in a marathon they never meant to run. Cuttlefish, by contrast, may seem brilliant. Masters of disguise with a brain-to-body ratio among the highest of all invertebrates, they flash color, texture, and pattern like underwater illusionists. But behind that display lies confusion. They sometimes flash mating signals at predators or camouflage against glass walls. Males disguise themselves as females to sneak past rivals, only to forget to switch back, confusing everyone involved. It's a magic act run by an animal that sometimes forgets which trick it's performing. Lurking under ledges is the moray eel, a paranoid, reclusive predator that lives in fear of everything. It spends most of its life hiding, biting anything that moves near its face, including allies like cleaner fish or even its own kind. With terrible vision and a trigger-happy bite, it lashes out first and assesses later. Sometimes not at all. And when it's not biting divers or panicking in a crevice, it's stuck inside one, having wedged itself so tightly it cannot escape. Not far off, the grouper hovers, massive, thick-jawed, and seemingly immovable. It is strong, capable of vacuuming prey whole. And yet, it is also weirdly passive. These fish often approach divers curiously, get bullied by cleaner wrasses, and botch their own ambush strikes by opening their mouths too early. For a top-tier predator, the grouper behaves like a sleepy toddler in armor, too big to intimidate, too slow to adjust, and too trusting for its own good. Finally, there is the Napoleonfish, a reef colossus with a tank-sized body and the attention span of a distracted goldfish. Known to forget mid-hunt what it was chasing, it bumps into coral, misplaces its clams, and sometimes courts the wrong species. It can live for decades and grow over 2 meters long, yet its behavior often oscillates between regal grace and befuddled missteps. It is not stupid, merely tuned to a slower rhythm than the accelerating chaos of modern reef life. Together, these species paint a different picture of ocean survival, one that challenges the assumption that nature only favors the sleek, the smart, and the strategic. In reality, evolution is not a competition for perfection. It is a test of adequacy. And being just good enough, or more often, just not bad enough to die, is a perfectly viable path to persistence. Many of these species are relics of earlier ecological systems, their quirks once harmless or even advantageous in slower, quieter oceans. Now, as human disruption reshapes their environment at unprecedented speed, their awkwardness becomes more pronounced, their flaws more glaring. Yet they endure. Through a combination of luck, biochemical edge, reproductive volume, and ecological niche, these marine misfits continue to haunt the reefs and pelagic zones like forgotten characters in an evolutionary play. They are cautionary tales wrapped in scales and tentacles, not failures, but anomalies that remind us that survival is often less about brilliance than it is about persistence, about finding a way, however clumsy, paranoid, overreactive, or forgetful, to make it through another tide. They are not nature's champions, but they are nature's proof that even in a world shaped by tooth and speed, there is room for the ridiculous. In the vast, relentless machinery of the sea, these creatures are the sputtering gears that somehow still turn.